All right, so in this fourth method, we're going to be looking at using the quadratic formula to solve quadratic equations. Right, and again, this is something you're familiar with from previous courses. You've seen the quadratic formula before. We've even been still using it within this unit itself, okay? But just remember that sometimes using the quadratic formula, it's a little bit more cumbersome. It may take you longer to use, and there's a little bit more room for error. So while it is something that can be used, right, you just really need to make sure that you are using it correctly, okay? So again, remembering that like you're square rooting the right thing, you're dividing everything by 2a, right? So you're evaluating this entire numerator here before you do your division by 2a, right? Putting things into your calculator correctly, because that's where you can see some mistakes being made, okay? But let's get into some of these examples. All right, so one of the biggest things to kind of talk about here with the quadratic formula is the idea of the discriminant, okay? And the discriminant is a very specific part of your quadratic, right, that can kind of give you some key information without having to do the entire formula, right? So the value of the discriminant is actually given by that b squared minus 4ac, right? It's that expression that's underneath the radical, underneath the square root sign in the overall quadratic formula, right? Now that discriminant can have a few different values. The discriminant can be positive, the discriminant can be calculated and be a negative number, or it could end up being 0, right? And the value of that discriminant is going to tell you something important about the types of roots or the number of x-intercepts that that quadratic function has, right? If you have a positive discriminant, right, so if when you calculate the b squared minus 4ac value, you get a positive number, you are going to get two different x-intercepts, right? Two distinct real roots. It's going to cross the x-axis twice. If, however, when you calculate b squared minus 4ac, and you get a negative number, you're going to have no real roots, right? Because if that's the part of the equation that's underneath the square root, you're going to be trying to square root a negative, which we know we can't do, and therefore you're not going to have any roots. It's not going to cross the x-axis, okay? If your discriminant is actually equal to 0, right, that means your quadratic is only going to have one x-intercept or one root, and it's going to happen to be at the vertex, right? Because again, when you look at that equation, right, and you're doing that, and let's maybe just take a look at it here, if we have this negative b plus or minus the square root of b squared minus 4ac all over 2a, if when we calculate this we get 0, you're going to get x is equal to negative b plus or minus 0 all over 2a. And when you add 0, right, negative b plus 0 is just going to be negative b, and negative b minus 0 is also going to be negative b, so you end up getting the same answer twice. Right, and that's why you only get one real root. Okay? Another important thing to note is if when you calculate b squared minus 4ac and that ends up being a perfect square, like 4, 9, 144, 100, right, 64, 81, if your discriminant is a perfect square, that means that your quadratic is going to have two real roots, but they're also going to be rational, which means you could have solved this equation by factoring. Right, so if you're ever wondering, can I solve it by factoring, you can just check the value of the discriminant, right, do a quick little check, plug in your values for b, a, and c, b squared minus 4ac, calculate that. If that number is a perfect square, you can go ahead and factor that. If it's not a perfect square, you would not have been able to factor it, and you need to be able to use the quadratic formula or completing the square to solve this quadratic, okay? So again, let's just use those discriminant values, right, to see what the nature of these roots are going to be, right? So let's check to see, okay, is this going to have 0, 1, or 2 roots, and what types are they going to be? So in this first example, A, right, we've got negative 2x squared plus 3x plus 8, which means our A value is negative 2, our B value is positive 3, and our C value is 8. So if we were to calculate the discriminant here, and we do b squared minus 4ac, right, that's going to equal 3 squared, right, because our b value was 3, minus 4 times a, which is negative 2, times c, which is 8. So what we get is 9 minus 4 times negative 2 times 8, which is negative 64. So 9 minus negative 64. So we're subtracting a negative there. So it's essentially like adding 9 and 64 and getting a value of 73. Okay? That's a positive number. It is not a perfect square. So this one is going to have two real roots, right? And they're going to be two different numbers, and they're going to be distinct, right, in that first one. Okay, let's take a look at the second one. So 3x squared minus 5x equals negative 9. Remember that when you're identifying your values of a, b, and c, you must have your equation equal to 0. So the first thing I need to do here is bring that negative 9 across the equal sign. So what I really have here is 3x squared minus 5x plus 9 is equal to 0 before I can correctly identify my values of a, b, and c. Right, which means now my a value is 3, my b value is negative 5, and my c value is actually positive 9. Right? Once again, I'll calculate that discriminant of b squared minus 4ac. So my b value is negative 5. Make sure you're squaring the negative, right? So if you're doing this on the calculator, put the negative in brackets. So negative 5 squared, b squared, minus 4 times a, which is 3, times c, which is 9. Okay? So that's going to be 25 minus 4 times 3 times 9, which is 108. Okay. And 25 minus 108 is very clearly going to give you a negative value, right? So that's negative 83. So that means that this concave up parabola will never cross the x-intercepts. There are no real roots. Okay, no x-intercepts. It does not cross the x-axis. Right? Finally, in C, again, we can still do these things with fractions, right? That's not something that we're fearful of. Again, it's in standard form. It equals 0. So our a value is a quarter. Our b value is negative 3. Our c value is, in fact, 9. Right? So again, we evaluate the discriminant of b squared minus 4ac. My b value, again, negative 3, ensuring that we're squaring the negative. Okay? B squared minus 4 times a, which is a quarter, times c, which is 9. Right? So negative 3 squared is 9. 4 times a quarter is 1. 1 times 9 is 9. So we get 9 minus 9 is 0. Okay? So that means that this quadratic here has one real root. Right? So it's going to have, if we were to factor it, it's going to have a vertex that's on the x-axis. Okay? So that's kind of using that value of the discriminant in this case. All right. So again, we can just kind of run through a couple examples here using the quadratic formula. Right? We'll probably just do a in this case, and we are going to leave our answers as exact values. Yes, I know we can round, right, and get a decimal approximation, but we're going to continue to practice our exact values as it's going to be helpful later on in this course. So if we look at a here, and we're looking at an equation 9x squared plus 12x equals negative 4. Again, the first thing to remember is that you've got two rules before you can use the quadratic formula. One, it has to be in standard form, so that ax squared plus bx plus c equals 0, right? And in that same definition, it has to equal 0, right? So we need to make sure that we bring that negative 4 over before we start identifying our values of a, b, and c. So 9x squared plus 12x plus 4 equals 0, which now we can correctly identify our values of a is equal to 9, b is equal to a positive 12, and c is equal to a positive 4. Then we can go about trying to calculate our x-intercepts using the quadratic formula. So x is equal to negative b, so negative 12, plus or minus the square root of b squared. So again, this is the part where we're evaluating that discriminant again. So 12 squared minus 4 times a, which is 9, times c, which is 4. Okay? And that's all over 2 times a, which is 9. Right, so we can start evaluating this. I'll start by evaluating the discriminant. Right, so 12 squared, that's 144 minus 4 times 9 times 4, and you actually get this value of 0. Right, so it's plus or minus the square root of 0 divided by 18. Okay, and then once again, like I kind of mentioned before, if we're adding the square root of 0 versus subtracting the square root of 0, we are just getting the same thing in that we get x is equal to negative 12 over 18, and that x is equal to negative 12 over 18, right? That same thing where it's just going to be one real root, right? And we can simplify those fractions such that both of those are divisible by 6, so it's negative 2/3, and again, that's the same thing of negative 2/3, okay? So because a ended up giving us just only one real root, we are going to do b as well, just so we can see that being able to express things as exact values here. Okay? Oh, I'm going to need to add a new page. So that equation is 5x squared minus 7x minus 1. So 5x squared minus 7x minus 1 equals 0. So again, it's in standard form. It's set equal to 0. Right? So I can go ahead and correctly identify my values of a, b, and c. A is 5, b is negative 7, and c is negative 1. Right? So again, I'm going to use my quadratic formula here. X is equal to negative b. So since b is already negative, it's negative 7, which will turn into a positive 7, plus or minus the square root of b squared, so negative 7 squared, minus 4 times a, which is 5, times c, which is negative 1. Right? That's all over 2 times a, which is 5. Okay, so like I said, that negative 7 will turn into a positive 7. That discriminant is going to be negative 7 squared, which is positive 49, minus 4 times 5 times negative 1, so like minus negative 20, so it turns into a positive 69, right? And that's all over 10. Now 69 is positive. We know we're going to get 2 real roots here, and it's not a perfect square, which means we are not going to get nice fraction, integer, or rational values, okay? So at this point, we are going to be able to split this up into 2 things, right? One x value is 7 plus the square root of 69 over 10. The other x value is 7 minus the square root of 69 divided by 10, right? This is what I mean when I say exact values. And then the only thing you're going to check is that what's underneath your radical. Is your radicand divisible by a perfect square? So you can simplify it. Is it divisible by 4? Is it divisible by 9? Is it divisible by 16, 25, 36, 49? No, it's not divisible by any of these things, so this is as simple as it's going to get. Okay? So that's leaving my answers in exact values. Okay? So let's move on now to where we would still solve using the quadratic formula, but now we need to come up with the equation ourselves. So here's our context. Leah wants to frame an oil original painted on canvas measuring 50 centimeters by 60 centimeters. Before framing, she places the painting on a rectangular mat so that a uniform strip of the mat shows on all sides of the painting. The area of the mat is twice the area of the painting. How wide is the strip of exposed mat showing on all sides of the painting to the nearest tenth of a centimeter? So that indication there means we are not going to need to use exact values. We can, in fact, round our values. Okay? But let's set this up. Best thing to do here is to try and draw the situation. You have an oil painted canvas, okay, measuring 50 by 60, so we can assume that that's a rectangle. So we can sketch that rectangle, right? And we know that those dimensions are 50 centimeters by 60 centimeters, okay? She's placing that painting on a rectangular mat so that a uniform strip of the mat shows on all sides. So she's placing it on a slightly larger rectangle such that the amount of mat showing is the same on all sides. So like this length here is the same as this length here, is the same as this length here, is the same as this length here, right? Now we're being asked how wide is that strip. That's the variable that we are trying to solve for. So we're going to label that x. All right? So that's our variable. Now, the other information that we've been given is that the area of the mat is twice the area of the painting. Now, we can find the area of the painting, right? Because we have the dimensions of the painting. We know that it's a rectangle. So the area of the painting is a rectangle, so length times width, which in this case is 50 centimeters times 60 centimeters, giving us a total area of 3,000 centimeters squared. So we know the area of the painting. We know that the area of the mat is twice that area, so 2 times 3,000 is 6,000. So we know that the area of the mat is equal to 6,000 centimeters squared. Okay? And what we need now is an equation that relates the area of the mat. Right? So if you were to think about trying to find that total area of the mat, well, that entire mat is also a rectangular shape that has a length and a width dimension. Okay? We know that this length down along the bottom, right, is at least this 60 centimeters, but it's added 2 strips on the other side, right? So x and x. So this length is given by the dimension 60 plus 2x. And the height, or the width of this painting, is 50 plus 2x. All right, so that's 50 plus 2x there. So that means that our expression for the area of the mat is length times width, which is 60 plus 2x centimeters, times 50 plus 2x centimeters. And we know that when we calculate that, we get a value of 6,000. Okay? This does look like it's in factored form, but I can't solve it like this because it's not set equal to 0. Okay? I can't just take each of those factors and set it equal to 0 because they're not. It's equal to 6,000. So my strategy at this point now is to expand those out and get a quadratic. Right? So that 50 times 60 is that 3,000. 60 times 2x is going to be 120x. 2x times 50 is 100x. 2x times 2x is 4x squared, and that equals 6,000. Okay? Now, once again, what we're trying to do here is solve for x, right? We want to be able to create a quadratic formula or quadratic equation that's in standard form and set equal to 0. So combine like terms where I can, right? So I've got my 4x squared, I've got 100x plus 120x, so that's going to give me plus 220x. And then I can bring this 6,000 over to the other side by subtracting it, and it's going to be minus 3,000 is equal to 0. Right? From here, I can use my quadratic formula. Right? You might ask, well, why can't I try and factor it? Well, you could. Let's do a quick check to see if I could have factored it before I go through all the work. If I evaluate my b squared minus 4ac, if I use my discriminant, what is that going to be? Right? It's the 220 squared minus 4 times a, which is 4, times c, which is negative 3,000. So 220 squared minus 4 times 4 times negative 3,000. Okay? And you get this value of 96,400. And were you to square root that to check if it's a perfect square, it is not. Okay? So that's not a perfect square, so I will have to use the quadratic formula. There's no point in attempting to factor this. Right? So then what I can do is just immediately go and solve for x. So x is going to equal negative b, so negative 220, plus or minus the square root of, and I've already calculated my value of my discriminant over here, plus or minus the square root of 96,400, all over 2 times a, which is 4 here. All right? So since I've been asked to do it to the nearest tenth, I don't need to keep this as an exact value. I am just going to get an approximation. So in my first solution, it's negative 220 plus the square root of 96,400 divided by 8. And in my second solution, it's negative 220 minus the square root of 96,400 divided by 8. So you have negative 220 plus square root 96,400 divided by 8 gives me a value of 11.31 centimeters. Okay? And in this one, the negative 220 minus the square root of 96,400 divided by 8, and I get a value of negative 66.31. Right? And again, looking at these in context, x is a distance from the painting to the outside of the frame, so it doesn't make sense for that to be negative, so we can disregard this answer. Right? It's what we call an extraneous root. It doesn't make sense in context of our problem. Right? But our 11.31 centimeters does. However, we're rounding to the nearest centimeter, so we can say in our concluding sentence that the width of the strip is 11.3 centimeters. All right? And we've now set up an equation and then solved it using our quadratic formula. Okay? And then questions that relate to quadratic formula solving are here in chapter 4.4, and from that last video on solving by completing the square, those are in chapter 4.3. Okay.